Okay. Let's go to Matlab, and can you see that clear? Maybe I should increase the font a little bit. I think somehow the font shrinked. There is the editor debugger fonts. All right. Okay, that's much better. All right. So I'm going to demonstrate how to do a Jacobi iteration method in 2D, and let's take a look at the process. So what I'm going to do is I'm going to use a image. So let me first show you what the image is. Where is Open Current Folder in Explorer? So I'm going to use this guy, this girl, this lady. I'm going to it's a 128 by 128 pixel image. I'm going to say this is the solution of our 2D Poisson's equation. Okay, let's load it in Matlab. Okay, that's fine. So we can see it's we're going to load it as a Lenna BW. It's a size 128 by 128 by 3 matrix. 3 is because it has RGB. We are going to finish. So we have this in our code. Okay, so let's say U exact. So we are doing like a manufactured solution. We know like we are manufacturing the exact solution is equal to I want to convert it to double Lenna BW column 1. So I'm just going to take the red the red part of the solution. Okay, so if I do IM show, well, I think I can do it here. Maybe not. If I do IM show U exact, I think I need to divide by 256 because let me actually do it. U exact is equal to U exact divided by 256 because in the integer format, the value of the color goes from 0 to 255. So in order to have it like in the proper floating point, going from 0 to 1, I need to do a division. Okay, just to make sure we loaded the right image, looks like we did, right? That's the U exact. Okay, so if this is the solution of the Poisson's equation, what should be my B? Let's say with 0 boundary condition. What is my B? What is my I have AU equal to B. If U is equal to that, what is B? Huh? Yes. 0. I mean, if so, I'm trying to solve AX equal to B, right? I'm trying to solve AU equal to B. So if I want to get a U that looks like the lady, what should my be? 8 times U, right? So let's compute 8 times U. Okay, and I said 0 boundary condition. So let me actually do something different. U exact, we know it's 128 by 128. So let's actually make it zeros 130. So I'm basically putting 2. I mean, I'm padding the matrix by 2 on both directions. And I'm going to do this again. U exact from 2 to n minus 1. 2 to n minus 1 is equal to that thing. So I'm only loading the image into the interior of this array. So if I am show it, it's going to be the same except for like you see a black like black frame around it. It's the boundary. All right. Okay. So how do we compute B? Let's say B is equal to same thing, 0 to 130. I'm gonna for I goes from 2 to 129. For j goes from 2 to 129. I'm gonna say, oh, I didn't define dx. Let's say dx is equal to, what do you want? 1 over 129. Okay, because the number of grid points is 130, right? So the number of spacing is 129. So if the whole domain is 1 by 1, then this is my dx. Okay, so let me do this again. B of I and j should be equal to what? What is A times U? Now it's the exercise of converting the matrix operation into a stencil operation. It's just the Laplace operator, discrete Laplace operator, I minus 1j plus ui plus 1j plus uij minus 1 plus u of jij plus 1. Oh, u exact, sorry. Copy, paste, minus 4 times u exact. Did I? Oh, u exact. ij divided by delta x square. Is it? What is Matlab square? This, right? Okay. I get always confused between Python and Matlab. Okay, and. Now, if I am sure of B, it's this. Okay. All right. So now, starting from now, let's pretend we don't know U. Okay. I want to solve for AU equal to B, and we only know this B. Okay. So let's do this. Let's do Jacobi iteration. Let's start with the 0 initial guess. So this is our initial guess. Let me make still I think I can make the font a little bit clearer. Okay. Oh no, I didn't intend to make that bold. I want to make this bold. Okay, good. So this is my initial guess, and I want to do U next. U next is my, so let's say initially U, this is U0. U next is going to be U1. Okay, and I'm going to follow this very iteration. Okay, I'm going to do for I goes from 1 to 129, for j goes from 2 to 129, U next, I and j is equal to minus delta x squared divided by 4 times the parentheses, which is bij minus the average, I mean the summation of all the neighbors divided by delta x square. Okay, and this parentheses, it should be u of I minus 1j, u of I plus 1j, u of ij minus 1, u of ij plus 1, right? That's the bad thing about a big font. So okay, so let me review this. So u next ij is equal to, this is 1 over b, like 1 over the diagonal part of the matrix, right? Times b minus the upper and lower diagonal part of the matrix times u. All right. Everybody agree with this? Any box I have? This is the most easy line to make a box. And. Okay. I have completed one iteration. I am sure of U next. Well, we see something, right? No, you don't. I see something on my screen, so let me multiply something, multiply by 10, so that maybe you can see it. Do you see it? Okay, we start to see something that kind of goes into the direction of the original solution, right? We see the contours at least. So that's good news. Let's keep iterating. So how do we keep iterating? We set U equal to U next, right? Because now U next is my I equal to 1. I want to go to I equal to 2, so I'm going to set U equal to U next. And I'm going to do the same thing for, I'm just going to copy these 4 things. Okay, I'm done. My U next now is at U2. And why don't we do that multiple times? So for k equal to 1 to 100, for example, okay, I'm going to iterate that for 100 times. U is equal to U next. And for I goes like this, right? Am I making any bug? And, right? So now if I type enter, I would be doing 100 iterations of the Jacobi iteration. Anyone wants to look at U next? Should we take a break before we look at U next? Okay, let's look at it. Right, we are starting to get the solution. Right, it's no longer just a contour. And let's do 1,000 iterations. Let's do 1,000 iterations. Yeah. Oh, I didn't update it. Thank you. So, thank you for detecting my bug. Okay, I am sure you next. Pretty good, huh? Okay, let's take a break before we come back to discuss the convergence of the iteration and errors.